Hello, this is a video about the Qibec 1-bit 1-instruction transistor CPU that you can see here, sort of, because I took all the logic boards like this one out. So all that's left now are two special boards, which is the display board that you can see at the front here, and the bridge board or module that you can see at the back. And the bridge module basically serves as an interface between the PC and the address and data bus and control bus of the CPU. And the display is basically completely separate from the CPU. It's just a display which can be controlled by the PC, or rather by the bridge module. And in this video, I'll talk a bit about, not in very much detail, about the protocol between the host PC and the bridge module, and related the protocol between the bridge module and the display module. So what you'll see is basically commands for the display module are sent from the PC to the bridge module and are then forwarded by the bridge module to the display module, like that. So before we go into start drawing stuff, this has a normal serial interface. Two of the pins, as you can see that at the front, are receive and transmit. That's a TTL level serial interface, like an asynchronous serial interface as you're used to. This one has basically also a serial interface, except there's a serial interface to the PC, except there's what is it? FTDI USB bridge chip in between the PC and the micro that you see there. So now let's take a look at the whiteboard, how what the CPU system basically looks like. And this is a familiar picture, or at least it maybe if you watched other videos which exist or may not yet exist. So CPU system plus RAM and ROM basically looks like this. You have a CPU. Well, let's take that for granted. The CPU in the middle, there's a ROM at the top, usually drawn at the top, at least in the case of this CPU in this video series. There's a RAM at the bottom. CPU has a branch input coming from the ROM, part of each ROM word. It has a program counter output which indexes the ROM. The ROM indexes the RAM. How this works is subject of another video. There is a data I/O pin, 1 bit wide, on the CPU that interfaces to the RAM. Furthermore, there's a write signal for the RAM in order to tell the RAM whether to read or write data. There is a clock input, and there is a reset input. Right? Clock and reset do the obvious things. Now, this project is about a CPU. So what I did, the choice that I made was to not focus on RAM and ROM and implement the RAM and ROM in the simplest way imaginable, or the simplest way I could come up with anyway. So instead of having an actual hardware RAM and ROM connected to the CPU, I chose to do the following. Instead of an actual RAM and ROM, from the CPU's point of view, it's happy talking to something that behaves, and also control signals, something that behaves like a RAM and ROM and control signals, right? So if you imagine a cloud around the CPU, or a bubble, which gives branch signals, receives program counter output, which gives the clock signal to the CPU, which controls a reset signal to the CPU, which receives a write signal, right? It behaves as a RAM, and can provide or receive a data signal. So let's assume this cloud behaves like RAM, ROM, and control signals to the CPU, right? Now the choice was made to not do this in hardware, but to do it in software. So what you'll see is that what you'll see in another video is that the PC is used to implement this RAM and ROM and control signal. So there's a serial interface between the CPU and an emulated RAM and ROM on the PC. it doesn't mean CPU doesn't actually calculate stuff. It is real and it works, except the RAM and ROM are not part of the project and are emulated on a PC, right? So, however, the CPU still has electrical interface to the rest of the system. As you can see, all those lines here, the arrows are electrical signals. 16-bit wide, 16-bit wide, 1-bit wide, 1-bit wide, 1 and 1, right? So there has to be some kind of a translation from software on the PC side and electrical signals on the CPU side. To do that, I made a special module for that, plug-in module called the bridge module. It basically wraps the CPU in an electric shell, so to say, and behaves exactly as RAM and ROM and control signals towards the CPU, but in the background. So this is a bridge. I call it bridge. That's this module sitting right there. Those are that red thing here. So on the one side it talks electrical signals to the CPU, these are digital I/O lines, and on the other side it talks USB to the PC. USB. What we'll talk about in this video a little bit is what the protocol between the between the PC and the bridge is, and what the bridge, well, how the bridge translates between the PC and the CPU. So that's what this video is about. So let's draw this a bit differently, a bit simpler, namely like this: CPU, bridge, and PC. As you saw just now, between the PC and the bridge is a USB channel. It's actually a serial channel. It has nothing to do with USB. It's just modern PCs don't have serial ports anymore, so I use USB. It's so much simpler. And between the CPU and the bridge there are digital signals. Right? So what the PC does basically is communicate with the bridge using a protocol, custom protocol. It's a master-slave protocol. The PC is the master, the bridge is a slave. PC sends a command and the bridge always replies with a reply to each command. So it's command toward the bridge, reply towards the PC, command towards the bridge, reply toward the PC. And the reply always matches the command. So for every command sent there's a reply back corresponding to that command. And I'll take a look at that, how that works. So let's draw something that resembles a little bit, resembles a sequence diagram or something like it. And let's take a look at what goes over the wire, so to say. Now remember that the CPU has as output a program counter and a write signal to the RAM, right? As input, see how that fits. As input it has a branch input and reset and clock. Unfortunately I'm right-handed, that is not convenient. And it has a D signal, so data bit for I/O. I hope you can read that a little bit. So as output signal the CPU has a program counter, the write signal for the RAM towards the RAM. As input it has a branch input coming from the ROM, which is shown in another video, a low active reset input and a high active clock input. And as I/O input it has the one single data bus, data bit, so to say, connected to the RAM, right? Bidirectional. So there are, for now let's say there are two different commands the PC can send to the bridge. And one is a reset command, which is typically sent at the start of a program or a new program. Reset, which contains a high time and a low time for the clock signal, because the bridge has to provide a clock signal to the CPU because it controls the, well, control lines to the CPU. So if this is one clock signal, then this would be T high, this would be T low, in units of 10 microseconds, I think. It's not a big deal. So the PC tells at the start of the program how fast the bridge should operate the CPU, basically. After that, it doesn't have to tell it with every instruction cycle, as we will see. In response to that, the bridge will write or drive, let's say write the signals to the CPU. So it will pulse low active reset input low for a little while, inactivate the clock input, and I think that's basically it. After that, I'll draw the arrow from the bridge, because the bridge is initiator of this action. It will read some signals, and the most important of which is the program counter output from the CPU, because that's essentially the start address of the program. And then the bridge will report the program counter back and a reset reply to the PC containing the program counter and a status, which can be non-zero for error and 0 for OK, basically. Details are not discussed here. So you only issue this command once, reset command. The bridge does its thing, resets the CPU, and the bridge sends a reply to the PC, and then the program can basically start. Now, at each cycle within a program, the PC sends a cycle command containing the value of the branch input for the CPU. How the CPU's inputs and outputs are connected to the RAM and the ROM is subject of another video, but let's just say the branch input is essentially part of the ROM word of the instruction. It's actually a field within the instruction, current instruction. It also sends the non-inverted value of the data bit coming from RAM. Right? So what the bridge does in response is again write the signal, so it would set the branch input to the value it just received. It would set the data input to the CPU. It would drive the data line towards the CPU with the value it just received, and it would issue clock cycles. Now, this is actually, in response, the CPU would perform one instruction cycle, right? After which the bridge would read the signals from the CPU, being the program counter again, right? And inverted data bit. But actually, inverted data bit is not really necessary, because this is so simple. The PC knows that every instruction cycle the data bit is inverted. That is that's the nature of this CPU, basically. So it can, unless the status indicates an error, it can assume that the data bit has been inverted, and it can update the data in its own RAM array. So what the cycle reply from the bridge to the PC contains is a program counter for the next instruction, and again a status. Right. Small note, I'm gonna write that here, because that's the only way, only area there's a bit of space left, I think. If you look at the clock cycles between the bridge and the CPU has a multi-phase clock. Internally it works with a multi-phase clock. How the subsystems work, well, actually what the function of each subsystem is within the context of the CPU is described in another video. It's not described here. And in that video, when explaining the dynamic behavior within the CPU of the interaction of the subsystems within each instruction cycle, we'll see how the multi-phase clock influences each subsystem. Now for short, it means that for each instruction within the CPU, the bridge has to send, or the environment, in this case the bridge has to send 4 clock signals. So 4 clock signals on the clock input of the CPU, right there, correspond to 1 instruction cycle. So this Is that correct? Something like that. This is one instruction cycle, consists of 4 external clock input signals. Cycles, right? Okay, not important now. What's interesting now is that the CPU performs one instruction cycle. Okay, so that's, well, one cycle is performed, the next cycle in the program is performed, and so on and so on. The PC continuously issues cycle commands towards the bridge configures the CPU does a cycle, bridge reads the response from the CPU and sends a response back to the PC does its thing, and again and again and again. So that's basically how it works. Now for something completely different, let's forget all this, let's focus a little bit on the display, just a little bit. This is not important anymore. This, if you look at this baseboard, well, there's a bridge module, all the logic is connected to the address and data bus and the control bus of the CPU. This module shares two functions. One is the display, most of the module is display, and one is the DIO latch. We'll ignore the DIO latch for now, treat it as if it has been removed with all the other IO modules, logic modules. We'll focus on the display, and this display is completely separate from the whole CPU. So it's just sitting on this board, but actually the CPU cannot access this display. Display is a serial interface which is much too complex for the CPU. So what actually happens is, to access the display, well, in another video it's shown how by using the emulated RAM and ROM, actually the emulated RAM on the PC, and memory mapped I/O becomes very easy, and virtual devices or real devices can be easily connected to the CPU by using memory mapped I/O. And one of the devices connected to the CPU using memory mapped I/O by the PC is the display. How this works is subject of another video, but for now let's say the CPU cannot access the display, but the PC can. And how this happens is, PC is not directly connected to the display, but is connected to the bridge module. It sends a command to the bridge module forwards it to the display, and the display does its thing. It's simplex communication. Display doesn't send anything back, it's just a dumb display, right? So the bridge module also communicates to the display module. Right, so we just talked about the whole communication between PC and CPU through the bridge. Now PC can also communicate to the display using the bridge, and what essentially happens is that the bridge forwards display commands. Oh, that's not bidirectional. The bridge forwards display commands to the display. So, and basically if we do the sequence diagram thing again, like that, remember that the display has something of a very simple serial interface, and essentially it only has one command, namely set pixel. And to keep it simple, it has, well, let's take a look, right? So to draw something on the display from the program running in the CPU, how this works is subject of another video, but eventually the PC decides that something should be written on the display, right? And by doing that, it issues a display command to the bridge with as parameters x coordinate, y coordinate, pixel value, right? And that's basically it. There are also some flags, namely clear, flag whether to clear the display, and there's a screensaver. So it's a flag whether to turn the screensaver on. It's like how to say, it's a screensaver is on, the PC can write to the display and it will actually update the display image, except the image is not shown. So if you if you turn the screensaver off, the normal image is shown again. This is not important actually. So what the bridge does is it sees that this is a display command, so it's not intended for the CPU, it's intended for the display, and it doesn't interpret this command but just simply forwards it to the display. Forward. Right? So in other words, this, if there are changes to the display protocol, the bridge is not affected at all. So the bridge simply forwards this command, whatever it receives, with the display command identifier to the display. And the display receives an X coordinate and a Y coordinate and a pixel value on or off, and turns the pixel on in the display. And the display is very subject to change. At this moment there's a 16 by 16 LED matrix. I think I'll make it a 8 by 8 LED matrix or something like that. But that's essentially how it works. And the display does its thing, right? And as a courtesy, the bridge sends a display reply back to the PC, but it's just a dummy reply to let the PC know that the bridge received the display command and forwarded it to the display. So that's basically how it works. And the bridge module, display module, will change probably in the future, because it doesn't look very nice, I think, right? And also there should be some buttons on here, because I want to make it the CPU work standalone, and having buttons on the front panel helps in that respect. The display can also function as a user interface, so not show what the program is doing, the CPU program is doing, right? But also like a scroll text and menu options or something like that. And this bridge module is it works now. I want to keep the same protocol between bridge and PC as already exists, because that's convenient and it works. But also I want to have an actual RAM storage on here, and serial EEPROM or something like that, where you can upload from the PC different program images and just run them by using buttons on the front panel. So the CPU can operate completely standalone. That's the goal. Right? So I hope this was semi-useful, and let me know what you think. Thanks for watching a lot. If you're interested, take a look at the Qibec site, that's qibec.org, also listed in the video description. And if you're interested, take a look at the other videos. Again, let me know what you think, and have a nice day, and goodbye.